Hello everyone, I'm Jack Hickish. Welcome again from me to the CASPER Toolflow Workshop 2018. So Adam mentioned that we thought about doing this when we had the community workshop last year. We thought about having a workshop where we encourage developers to get involved in the tool flow and maybe try to teach them a bit about how it worked. I think when I had that conversation, I was envisaging, 4 people in a dark closet in the SKA office. We're now in an observatory. I have a microphone on my face. I'm wearing a shirt. Needless to say, this has got wildly out of control. And then I thought about it, and that's actually probably quite appropriate because we're all here discussing a tool flow that was written a few years ago in a basement in Berkeley, largely just so that I could program snapboards to be used in Hera. And since then, that too has got wildly out of control. So we'll just roll with it and see what happens. So Adam asked me to give a talk and then told me it was going to be filmed, which is great. So I threw something together, mainly just stating sort of the problem that we have in radio astronomy, I think, as a community that we're trying to address as CASPER, and how we sort of converged in a slightly Brownian motion type way on the CASPER toolflow, which we have today, and which maybe, hopefully, some of you will start using in your work or contribute to. So I think we all know, those of us that build instruments in radio astronomy, that astronomy is now a supercomputing science. We've gone from using sort of curved bits of metal to focus electromagnetic waves to using computers to add together electromagnetic waves in a coherent way, starting with big dishes, going to big arrays, going to phased arrays, potentially with many hundreds or thousands of inputs. Scientists are pesky. They keep wanting more stuff. They like more bandwidth, they like more field of view, they like more sensitivity, they like more resolution in just about every dimension they can think of. That lands us on this sort of Moore's law growth of instrumentation power. You can look at, in correlators, the number of baselines times the bandwidth and see this sort of exponential growth. You can look in spectrometers at the number of frequency channels which our instruments generate and see this exponential growth. You can look at what the numbers are today that we typically work with. So in terms of number of antennas, we may be at 1 for a large disk to 1,000, something like Chime. And there are many arrays sitting in between those values. Hera, that I work on, has 350 antennas. Meerkat, of course, based here in South Africa, has 64. Bandwidth, similarly, can go from a few hundred megahertz up to sort of tens, maybe 100 gigahertz, and the number of frequency channels from thousands to millions or billions if you're doing something like a SETI experiment. In terms of time resolution, again, depending on your science goal, you might be happy with very slow images of the sky. It's sort of second cadence. You might want really fast images to look for transient events. And all of these things add up to make many, many terabits of interconnect and many, many complex tera operations or peta operations per second. But that's fine. Astronomy's hard. It's supposed to be hard. That's why it's fun. Luckily, when you look at the instruments we build, they are sort of at their heart quite simple. So for example, if you're building a spectrometer, you want to start with an instrument that reflects this block diagram. You digitize some signals, you do some sort of filtering, some sort of FFT, cut it into frequency channels, take the power, average it down, write it to disk, you're done. It doesn't matter whether you're using the biggest dish in the world, whether you're using a TV antenna in an undergraduate student project, roughly speaking, all looks the same. If you want to go to an array, well, you reuse some of the blocks again. You have the same ADCs, the same kind of filtering. Now, rather than taking simple powers, you multiply antennas together, cross-multiply them, average those down, write them to disk. Again, sort of the block diagram is kind of simple. We reuse a lot of parts, all good. Perhaps you don't want to implement your interconnect using lots of cables. Perhaps you want to use an Ethernet switch. Again, the block diagram's very similar. You've now just replaced the interconnect part of your system with something that you buy off Amazon, or in my case, off eBay. So what is the problem? Because it all looks easy, and it's sort of that, well, conceptually, radio telescopes are quite simple. You digitize some signals, you cut them into frequency channels, you combine them in some way. Maybe it's beamforming, maybe it's correlation. depending on what your end goal is. And you can describe the system you're trying to build with a block diagram, and the block diagram is quite simple, and all telescopes have the same block diagram, and we're really good at implementing the individual blocks. Many of us, myself not included, can happily knock out like a really effective Fourier transform module or a really effective filter module to be run on an FPGA or something. So why is it still so damn hard to build an instrument? Why does it take so long, and why is it so expensive and time-consuming? Makes me crazy. And so enter the Center for Astronomy Signal Processing and Electronics Research, CASPER, Center meaning Berkeley, California. That was re-acronymed some years ago to Collaboration, which was really an acknowledgement that most of the work doesn't happen in Berkeley. In fact, I think it's fair to say that most of the work for many years now has happened here in South Africa and been driven by the Meerkat developments. I think I would argue for re-acronyming it again to community, reflecting the fact that collaboration, I think, implies that we're all headed towards some common goal. I think really the case is we're all headed towards our own goal and hopefully helping each other out along the way. So if you've ever been to the CASPER Wiki or been to any of Dan Wertheimer's self-help talks, you'll know that the primary goal of CASPER is to streamline and simplify the design of radio astronomy instrumentation through design reuse and using platform-independent open source hardware and software. What does that mean? Well, given that the block diagrams of radio telescopes are simple, you should be able to make a simple tool to turn those block diagrams into physical manifestations of instruments. You should be able to reuse hardware, reuse software, reuse processing modules, interfacing software libraries, all of that stuff. And you should be able to reuse intellect. All of this stuff should be open source. And open source in the sense that it's on GitHub, warts and all, not open source in the sense that it was written up in a scientific publication, and if you know the right person who knows the right person, you can get the code. Actual open source. So in terms of developing general purpose hardware, having people reuse it, the collaboration's been pretty successful over the last decade. We've been through a few series of boards designed by different groups. So the B2 was a Vertex 2 Pro based board, then came the iBob, which you could plug some ADCs into and would spit out Ethernet traffic. Then came the Roach, which was designed again to feed ADCs into and spit out Ethernet traffic. CASPER centered around this idea that you always want to go into some industry standard communications protocol, so most of our boards ultimately spit out Ethernet. Roach 2 came along, again designed largely by collaborators in South Africa. Similar board again, Ethernet out, ADCs in. Then came Snap, which was in fact the board that spawned the Toolflow that we currently use. This board was designed for HERA, where we had the need to digitize a few hundred signals at about 100 or 200 megahertz of bandwidth. And so basically what we did is we took the Roach board, an ADC mezzanine card, and an FPGA processor, munged it together onto a single board, put a cheap FPGA on there instead of the Roach 2's expensive FPGA, and landed here. Somewhat at the other end of the spectrum, much more powerful board is the Scarab, which is, of course, the main processing element used in the Meerkat array. And other collaborators have contributed boards, which are supported to some greater or lesser extent at the Toolflow. The Snap 2, similar to a Roach, general purpose, lots of I/O, lots of generic memory interfaces, and space to put in digitizers. So getting people to use the same hardware is one thing. You can just build it, create a community around supporting it, create a mail list where people answer questions about the hardware. And that, it turns out, gets you a large way through the problem of everyone going off and doing their own thing, spending lots of money on R&D. You also need some libraries that support these boards. So we have in CASPER a large signal processing library made up of these Simulink blocks, which essentially encapsulate some sort of DSP operation. So this is the FFT, the fast Fourier transform block. I think largely written at this point by Andrew Martins, maintained certainly by Andrew. And in Simulink, it's nice, it's user-friendly. You type in the sort of parameters you want your FFT to have, and then it goes and does that operation to your data. Nice, easy. So you have the common software libraries, you have the common hardware. Unfortunately, that still doesn't really really get you through the problem that turning these block diagrams into physical manifestations of instruments you can deploy is still tricky. And this is kind of what the Toolflow aims to solve. So, and the problem, of course, is that you take an FPGA, this is the Roach2 block diagram, there's a bit you care about, which is all of the multipliers and RAM blocks and lookup tables that you're going to turn into an FFT. And that's great, you know, an astronomy postdoc or a student can get their head around that. They know what they want to interface with that circuitry the FPGA provides. Unfortunately, suddenly they become responsible for all of this other nonsense which no one wants to know how to use. So you can't use an external memory chip without instantiating a memory controller. You can't use an Ethernet interface without instantiating all manner of clock infrastructure and buffering infrastructure. You can't talk to your design unless you have some sort of software process running somewhere to accept commands and feed them into your FPGA fabric. And that stuff is all pretty complicated. You know, anytime you want to pull out one of the bits of Xilinx IP that corresponds to one of these interfaces, that's a 50-page or 100-page document right there that people in an astronomy department have no interest in reading. So comes the CASPER Toolflow, and the goal of the CASPER Toolflow was to make FPGAs commodity signal processing platforms in much the same way that GPUs have become commodity signal processing platforms via CUDA and Python libraries, PyCUDA, that kind of thing. So the goal is to hide everything that the users don't care about, all of the implementation details. That's like 90% of the difficulty in FPGA programming, dealing with clocks and buffers and asynchronous data transport between one place and another. Simplify the DSP design for the bits the users do care about, which is where all of the DSP libraries come in. And then simplify loading the design onto the board and interacting with it. You know, if I've made a design with some registers in, it should be easy to write values to those registers or read values out of those registers. So in terms of what the CASPER Toolflow actually is, well, in its past, it was a big MATLAB object-oriented programming-based infrastructure to generate code. Now it's a big Python object-oriented programming infrastructure to generate code. So the idea is, you know, your user designs in Simulink, they move around blocks, they join them together, and then some Python takes over and somehow knows how to turn blocks that really encapsulate quite complicated processing, like, for example, an ADC interface or a high-speed Ethernet interface. And Python can take over and sort of deal with instantiating the correct infrastructure to make these blocks work. And then the other nice thing the Toolflow can do is bundle any information about registers which the user wants to be able to read and write at runtime into the bit stream in such a way that your software library, which you later use to talk to the board, can magically know how to interface with it. So what does this look like? Well, it looks like a Simulink model at the front end as far as the user is concerned. So this model is simply one that has two ADC boards connected to something like a Roach2 and feeds their data into some snapshot blocks. So this design is a simple ADC to data capture. You can capture small bursts of data. And the idea is with the CASPER Toolflow, you start with this that makes sense to most people. You hit go. By the end, you get a file, an FPG file in Casper's case, which you can load to a board like this with a Python library and immediately start reading data. And everything should be that simple. So the Toolflow intends to be, whether or not it succeeds is I guess, for you to vote on, low overhead for HDL developers, which is to say, if you can build an ADC interface in Verilog or VHDL, it shouldn't be massively difficult to then crowbar it to work in our infrastructure. It should be relatively straightforward. The Toolflow tries to be not too clever. That's not too difficult because I'm not that good at Python. And also it tries to be kind of community-oriented in the sense that there are a few people that contribute to it, and I think we place a focus on getting new hardware supported, getting new features into the Toolflow, not fighting over whether everyone has correctly followed like PEP 8 style guidelines. More concretely, and I think that's what we'll be talking about this week, how do you support a new platform? Well, if you imagine you start with a board completely from scratch, you start with a board that had nothing to do with CASPER, but you know its schematics, you know its pinout. Well, the first thing you do is write a YAML description of that platform which the Toolflow can understand. So this example is for the snap board. So, and I should say there is documentation for this online. Hopefully most of the fields are fairly self-explanatory. This board is called a snap board. That's our friendly name for it. It has one of these Kintex 7 FPGAs made by Xilinx. When you compile for this board, you should probably compile with Vivado rather than, say, Xilinx ISE or Altera Quartus or anything like that. The board has 2 SFP ports. It has 1 ZDoc port. And just the head of a large definition of pins, it has these LEDs. So sitting at physical FPGA pins with an LVCMOS 2.5 I/O standard are some LEDs. And again, the pins definition goes on to basically give friendly names to all of the pins in the design. And the idea would be that from a designer's point of view, I want to say in my design, connect this signal to LED 0. I don't really want to have to worry about saying connect this pin to C13. You know, that's really the job of the Toolflow, not the user. Having designed your platform, then you need to figure out what that platform requires in terms of infrastructure that you would put in, say, a top-level HDL description of a design targeting this board. So for Snap, we create an infrastructure block which takes in an external clock. I believe for Snap, that clock is at 200 megahertz, and it delivers a system clock to the board, which is at 100 megahertz, which various other blocks can use if they so choose. And all of this orchestration is carried out by these fairly simple yellow block classes. They're called yellow block classes because in Simulink the blocks are physically yellow. That terminology, I think, will stick with us until we die. And there really isn't much you have to implement to get a platform off the ground. So for example, for Snap, we start with an initialize method. We tell the Toolflow what source files it needs. Yours might be different. You may have more of them, but probably there'll be some sort of infrastructure module. There's then a modify top method. This is a sort of Pythonic interface to some Verilog module. And so in our case, this Verilog module is the input argument top. And we can add things to it with the Python. So we can instantiate this Snap infrastructure module. We can define what ports it has. We can define what those ports are connected to. We can define whether or not they're promoted to ports at our top level, which go on to be physical pins, or whether they're ports that just are for interconnections within the HDL module itself. And then finally, we need some constraints because we're using real physical pins. We're generating clocks. And so there's sort of Pythonic wrappers telling the Toolflow that these pins called sysclock N, sysclock P should be connected to some pins which have friendly names which we've defined in our platform YAML file. In this case, they've got the same name, sysclock N, sysclock P, and a clock constraint which tells the Toolflow, hey, this pin is also a 200 megahertz clock. So you can probably imagine this can get more or less complicated depending how straightforward or complex your platform's infrastructure is. But pretty much these 3 methods cover most basic use cases. Having got the ability to compile for a particular platform, having implemented the infrastructure that platform needs, you probably want the ability now to have other interfaces that are instantiated when the user puts yellow blocks in their design. So for example, for Snap, we want the users to be able to use the ADCs. So if you grab an ADC block and put it in the design, you want the Toolflow to automagically figure out what it should do. And so again, there's a similar yellow block, this time representing an ADC. It requires a bunch of sources. It requires some interface code. It requires a FIFO generated with Xilinx CoreGen. But ultimately, we can instantiate this thing just by doing these things which are defined in the modification method. And just like the Snap infrastructure block, your ADC probably comes with a load of constraints. In our case, it's a ZDoc ADC, so the ADC data pins, these data even, data odd, should be attached to physical pins on the ZDoc port. So the port is defined by what the user has selected. When they drop an ADC yellow block in their design, they can say, do you want it to be on port 0, or port 1, or some other port? And then you can define in Python how you want the pins in your top-level ports to be mapped. So that's defined by the design of the ADC, how it utilizes the ZDoc pins. And again, the idea is this level of abstraction means that any board which has defined in its platform configuration file ZDock pins can now instantiate this ADC, and all of the pins will just end up in the right places. And then the Toolflow whirs away behind the scenes and ultimately takes these Pythonic definitions of stuff, of source files, of HDL instances, of constraints, and turns it into a Vivado project. So it generates a big old tickle script, which essentially starts a project, imports some files, and starts doing stuff. And there are many ways to get more advanced sort of tickle commands into this project creation script. But the bulk of the work is hopefully done by these methods that just tweak the top-level Verilog and set constraints. And then hopefully it delivers you a file that, again, you can do this with. You can just program with your CASPER FPGA programming package and start playing with. The Toolflow has quite wide usage around the world. This map mostly shows Roach 2 users who use a previous version of the Toolflow that largely attempts to solve the same things, does it in a more MATLAB-oriented way rather than a Python way. But it turns out, if you start with a bunch of hardware platforms that are well supported, well available to the community, and a bunch of DSP libraries that, again, are well supported, and a Toolflow to turn them into instruments, you get immediately quite good acceptance within the community. There are most telescopes now around the world. If you go and walk into their data centers, you'll see some amount of CASPER hardware being used there. Traditionally, our problem has been that while we have a lot of users, we have very few developers. I think you could count on one hand the number of people that could add a new platform to the old MATLAB-based Toolflow or add a new yellow block. Now you can probably count on 1.5 hands the number of people who can do that. Hopefully, by the end of this week, we'll be past the hand-counting regime of developers. But I will be here for the next week, walking around trying to help answer questions about the nitty-gritty of the Toolflow that obviously I just swept under the carpet for the purposes of this presentation. Just if you wanted some motivation to start using CASPER stuff and making your stuff available to the community in the form of CASPER Toolflow support, there are many dozens of instruments that have been using snaps and Roach 2s and scarabs over the past decade. Everything from $100 million projects like Meerkat to multi-million-dollar projects, Paper, Hira, to student experiments, things that grad students do like Fly's Eye, and as well also using CASPER hardware to do development studies at places like ALMA, where traditionally there would be no chance of putting anything but the most custom designed hardware up at that site. And I think that probably brings me to a close, and I will take any questions, or we can just go and have lunch.